Okay, so we'll go ahead and finish up 7.8 here. We talked about the two kinds of improper integrals. That's where you have an infinite interval and an infinite discontinuity, so like a vertical asymptote. Okay. The last thing in this section is information on the comparison tests for improper integrals. Now, this is going to be important for later on when we get to chapter 11, because in 11.4, when we talk about series, there's a section called comparison tests. Okay, and we'll look at that one once we get there. But so this is kind of a preview to things later down the road there. But here's what the comparison test says for improper integrals. Let f and g be continuous functions, and suppose that f is bigger than g for all x bigger than a. So I got a picture here. Here's f of x, and here's g of x. Here's a, and anything that's bigger than a means that f of x is bigger than g of x. Okay, so suppose we have that. Then if the integral going from a to infinity of f of x dx converges, well, something smaller than that is going to be also convergent. Okay, so the integral going from a to infinity of g of x dx, that's also going to converge. Okay, and convergent again just means that the limit exists. Okay, you have a finite number. Okay. Item 2, if the integral going from a to infinity of g of x dx diverges. So suppose that this is an infinite region. Well, anything bigger than that is also going to be an infinite region. So the integral going from a to infinity of f of x dx, that's also going to diverge. Okay? So as an example, I got two examples here, but for this first example, we're going to show that the integral going from 0 to infinity of e to the negative x squared dx is a convergent integral. Okay, now this is an important integral in statistics. This is, if I look at the curve, y equals e to the negative x squared, that would be the bell curve, the famous bell curve that we see in statistics. So I want to show that this integral here is convergent. Okay, now I've got to note, you can't integrate the integral directly because the antiderivative of y equals e to the negative x squared is not an elementary function. Okay, so in other words, if I did not have bounds on there, that would be an impossible integral to integrate. Okay, now I'm not going to integrate it directly. Okay, so all I want us to do is to show that this would be a convergent integral. Okay, so to do that, we're going to use a comparison test. The integral going from 0 to infinity of e to the negative x squared dx, so I'm going to go ahead and split this at 1. That's the integral going from 0 to 1 of e to the negative x squared dx plus the integral going from 1 to infinity of e to the negative x squared dx. Okay, now I have the graph of y equals e to the negative x squared shown. That's this bell curve there. Okay, and I'm going to compare e to the negative x squared to e to the negative x. So, by the way, it's common for us to compare functions, if we're looking for the function to compare it to ignore powers or things that we're adding or subtracting. That's typical. Okay, so for this one, I'm ignoring the power of 2. And here's y equals e to the negative x. Okay, now you can see that the first integral on the right is going to be convergent, right? Because I have a finite region here. This is enclosed. And for the second integral on the right here, we're going to use the comparison test. Okay, So I'm going to have us compare e to the negative x squared to e to the negative x, only for when x is bigger than 1. Okay, now you can see from this graph here that e to the negative x is always going to be larger than e to the negative x squared, as long as I have values of x that are bigger than 1. So like if x is 2, e to the negative second, the same as 1 over e squared. If x is 2 over here, I got e to the negative fourth. That's 1 over e to the fourth. Well, 1 over e squared is going to be bigger than 1 over e to the fourth. Okay, that's for when x is 2. So, well, let's see. I'm going to go ahead and integrate this function, y equals e to the negative x, on the interval 1 to infinity. That's an improper integral. So I need to use the limit definition. That's equal to the limit as t approaches infinity for the integral going from 1 to t of e to the negative x dx. And the antiderivative of e to the negative x is negative e to the negative x going from 1 to t. And let's see, when I plug in my bounds here, I'm going to have e to the negative first power minus e to the negative t. Okay? Let's see, from that, I have, by the way, so I've got these switched here. So it's negative e to the negative x, right? But if x is t, I got negative e to the negative t. And if x is 1, I am subtracting a negative, so that really means I'm adding e to the negative first power. Okay, so now t is approaching infinity. E to the negative t, the same as 1 over e to the t. So if t is approaching infinity, then the denominator is going to be growing without a bound as the numerator just sits at 1. Okay, so that is going to go to 0. And limit of a constant is always the constant, so I'm going to get e to the negative first power. Okay, well that's a finite number, right? So this region here, going from 1 to infinity underneath the top curve, is a finite region. Well, anything less than that is also going to be finite. And so I kind of wrap up this argument here. Since the integral going from 1 to infinity of e to the negative x dx converges, that's what we just used, then anything smaller than that, then the integral going from 1 to infinity of e to the negative x squared dx, that's also going to converge. Okay, and I'm adding another convergent region. Okay, so convergent integral plus a convergent integral, that will always give me a convergent integral. So therefore, the integral going from 0 to infinity of e to the negative x squared dx converges. Okay, so I showed you that this integral converges, but we didn't find what it converges to, right? That's an impossible problem, okay? Because you can't integrate this function directly, okay? But we still showed that it's a convergent integral, though. Here's another example. So let's see. Suppose that we want to integrate the function, which is the square root of x to the fourth plus 1 divided by x cubed dx on the interval 1 to infinity. Okay, I want us to show that this integral here, this specific one, is divergent. And we're going to use the comparison test. Okay, so I need to find something to compare this to. Well, if I get rid of the plus 1 there, okay, well, the left side is always going to be bigger than the right side if I'm adding 1 in the numerator, right? So the square root of x to the 4th, that's the same as x squared. And I have x squared divided by x cubed. That's the same as 1 over x. And the integral going from 1 to infinity of 1 over x dx, that's a divergent integral. That's one of our p-values that we did right here. Okay. Let's see. If that's a divergent integral, then anything bigger than that is also going to diverge. Okay, well, the square root of x to the 4th plus 1 divided by x cubed, that's bigger than 1 over x. I'm integrating on the same interval here, so that's also going to be a divergent integral. Okay. Again, the comparison test, so this is kind of like a preview for things down the road. The comparison test is important for when we get to series, and I'll have a lot more to say once we get there. So this is kind of there's a couple of homework problems at the end of this section that involve the comparison tests. So again, if you're finding the function to compare it to, number one, it's got to be a function that you can integrate, or that you know what the answer is, whether it's convergent or divergent. And number two, it's got to look very similar to the function that you're given. Okay, so like this one, is very typical for us to ignore things that we're adding, or like up here, am I ignoring this power of 2? These are very similar to each other. Okay, and that's the trick. But I'm not looking for some mystery function that I have no idea what the integral is. That totally defeats the purpose of using the comparison test. So you're comparing this to something that you can get your hands on. Okay. All right, so that's it for this section and the chapter. And so have a look at the homework problems that are on page 549 there.